So now we continue on to 9b, where we will look at the homogeneous Poisson process in terms of the first definition we encounter from the book. They ask us then to find the probability that the claim number at t1 is greater than 1, and the probability that the claim number at a later time t2 is greater than 2. Now, since we are assuming the properties of definition 2.1.1, let us just recall what that will imply in our case. So first of all, based on definition 2.1.1, we will know that n of t1, so the first thing that we're looking at here, is Poisson distributed. And since we're looking at a homogeneous Poisson process with intensity lambda, the number of claims that we observe from time 0 to t1 will be Poisson distributed with expected value lambda multiplied by t1. And also, n of t2, well, that will consist of n of t1 plus the increment that we experience from time t1 to t2 in claim number, where the increment in claim number from time t1 to t2 is first and foremost independent of n of t1 by the independent increment property from definition 2.1.1. Secondly, the increment will also be Poisson distributed. With which parameter? Well, lambda multiplied by the time interval length that we're looking at. So multiplied by t2 minus t1. So now we've written up more or less everything that's worth knowing. Maybe it's also a good idea, just for fun's sake, to write up for m, which is Poisson distributed with some parameter. Let's just call that parameter alpha, for example. Then the probability that m is equal to k is given as e to the minus alpha multiplied by alpha to the k divided by k factorial for k equal to 0 or 1 or 2 or 3 and so on. So now I think we've recalled more or less everything that's worth noting, so we can start calculating. So with the same idea as we always have, we try to look at the event that we have given at hand and say, well, can we split it up into something that is useful for us? Can we split it up into something that we can use? Oh, sorry, I think I forgot to write greater than equal and greater than equal here. Yes, this looks a bit more right. Okay, so can we split this up into something that is easier to work with? Well, let's just think about what happens if n of t1 is equal to 1. Yes? Well, if n of t1 is equal to 1, then n of t2 minus n of t1 is only greater than equal to 2 if n of t2 minus n of t1 is greater than equal to 1, right? So that's the case we have for n of t1 is equal to 1. Then the only way we can include the event up here is if the increment from t1 to t2 exceeds 1. Now, we also have another case where we think, well, n of t1 does not necessarily have to be equal to 1, because in the event we're looking at, we require n of t1 to just be greater than or equal to 1. So if it's not equal to 1, then n of t1 will be greater than 1, strictly greater than 1. In that case, well, n of t2 will also be strictly greater than 1, hence greater than equal to 2. So the event that we have up here, if you think about it, we can split it into the union of two events. First, the event that if n of t1 is equal to 1, then the increment from t1 to t2 must be greater than equal to 1. And then the other event that if n of t1 is greater than 1, then we need not impose anything on n of t2, because then n of t2 greater than or equal to 2 will be an event that is included already in the event that we're looking at here. So the probability of this thing happening is just equal to the probability of n of t1 equals 1, and that the increment is greater than or equal to 1, plus the probability that n of t1 is strictly greater than 1. Now, what do we have for the next step? For the next step, we can take a look at what we recalled from the definition of Poisson process. Because for the first term, what we have is n of t1 and then the increment from t1 to t2. And the increment is independent from n of t1. So we may factorize that probability into the probability that n of t1 is equal to 1, multiplied by the probability that the increment of n from time t1 to t2 is greater than or equal to 1. And then onto that, I add the probability that n of t1 is greater than 1. Now we're actually more or less done, because the probability that n of t1 is equal to 1, well, that is given by my point probability in a Poisson distribution where the parameter alpha has value lambda t1. So this first term is given as e to the minus lambda t1 multiplied by lambda t1 to the first, as such. Now my next term, I want to find the probability that this stochastic variable takes on the values 1, 2, 3, and so on. So it can take on any value except for the value of 0. So I want to find that probability. Now that is just the probability of it taking on any value, which is 1. The probability of that is 1, minus the probability that the increment is 0. And I find that probability by plugging 0 into the Poisson distribution's point probabilities, where I look at the Poisson distribution with parameter lambda t2 minus t1, right? So that is e to the minus lambda t2 minus t1. And then onto that, I have to add something. I have to add the probability that n of t1 is greater than 1. So that means that n of t1 can take on any value. So the probability of that is 1. Minus the probability that n of t1 is equal to 1, because we can't allow that. And that is e to the minus lambda t1 lambda t1. And then minus the probability that n of t1 takes on the value 0, which is minus e to the minus lambda t1. Right? Okay, so now I have written up this probability. And if you felt that was a bit confusing, then please just write down this expression that is up here, and just look at it, and look at it, and look at it until you are able to calculate this thing that's down here. And the reason why I say that is because these are some of the calculations that you need to be able to do without spending too much energy. So just look at it until you get the calculation. Now, this thing, well, what is it equal to? First of all, we see that some terms cancel. This term here cancels with this term here. So we have 1 minus e to the minus lambda t2 multiplied by lambda t1, where this term comes from this term multiplied by this term, yes? And then minus e to the minus lambda t1. And this is the expression, again, as we recall, that we now have found for the probability that n of t1 is greater than or equal to 1 and that n of t2 is greater than or equal to 2. Now, very interestingly, this expression is equal to the expression that we found for the joint distribution function of T1 and T2 in A. So we have more or less reached the conclusion that we wanted. And then you might say, wait a second, what about the probability we need to find of, well, the probability that n of T1 is greater than or equal to 1? What about that? We haven't found that yet. Well, to that, my only answer is you're able to do that quite easily on your own, so just do that on your own. And you'll also realize that this probability that n of T1 is greater than or equal to 1 is exactly equal to the probability that T1 is smaller than or equal to the time T1. So now we have reached the conclusions that we wanted to reach in this exercise. I will leave C to yourselves, partly as a kind of just think about it a bit philosophically. Think about what I said in the introductory video for exercise 9 and look at the PDF solutions, and you'll have more or less a clear picture of what's going on in C. So that was exercise 9, and I will upload exercise 10 at some time in the near future. See you guys.